copy, which is a useless exercise. So in short, beware of representing structs, which CG_point is, as anything other than a local instance variable. All right, so now scrolling down, we've prepared Tommy. I've got a handle pan method. I've got a handle pinch method. I've got view did load. Let's look there then. So again, when reading through someone's UI type code, start with the app delegate, move on to an init method, then look for something like view did load. So what do we have here? Same code as before. I'm listening for a pan or I'm listening for a pinch, and so this code is structurally the same as before. I'm saying inform me, self, specifically passing in the handle pan message or the handle pinch message. And how do we do this? Well, now unfortunately there's some math involved, which is sort of interesting, but besides the point for how the code itself is designed. So we'll wave our hands at some of these details. But this is how we now start doing, these sexy sort of capabilities of these devices. So if handling a pan, so if I want to translate Tommy, that is shift him right, left, up, or down, I have to actually start doing some math here. So in order to figure this out, for today's purposes, let me go ahead and wave my hands at this, but point out some of the salient structures. So we have a CG affine transformation struct here. We have a CG point. We have this helper function here, transformation concat, to actually concatenate, essentially do matrix multiplication. If this is unfamiliar or completely rusty, don't worry. It's doing transformations essentially follows this kind of boilerplate code. But ultimately, what we're trying to do is shift Tommy's location by some number of points on the x-axis and the y-axis. And we can figure this out by asking the sender. And let's see where we use sender in here. We can ask the sender exactly what what the shift has actually been. So in other words, we're passed a pointer to this recognizer. The recognizer is going to inform us how far the human finger dragged, and we can then use that to infer the mathematics of translating Tommy as a result, so that he effectively follows our finger up, down, left, or right. And pinching is very similar, but instead of translating him, we're instead going to update his scale and thus the size of the image that's actually being displayed. All right, but more fun than scaling Tommy is to actually implement something like Pong, which I promise you 30 years ago was a really cool game. So let's start with these last of two. Let's implement a little paddle. So this is a little paddle example that's not going to do a huge amount of interest, but it does implement the first application where we're not actually doing just standard UI widgets. So if pretend the arrow is my finger, I now have the beginnings of a game called Pong. And for those unfamiliar, there's going to be a ball eventually that's going to bounce left to right, top to bottom. And the goal is with these white paddles to make sure it doesn't pass your goal. Otherwise, you lose a point. So there's something interesting going on here where I'm detecting the key press. And I'm actually translating the position of this little rectangle to match whatever that is of the arrow. I'm apparently ignoring left-right movement, but I am responding in lockstep to up-down movement. So let's see what's going on here. Well, notice in my nib file for this paddle example, all I've done is create the background here. I just made it black, and that's it. Because I decided here that I don't want to use a static image for the paddle. I can draw it myself. And indeed, we can see how to draw something as follows. I went ahead with Xcode's file menu, and I created a new object, an NS object, or rather a UI view object, which descends from NS object, and I called it paddle view. So in other words, my goal was programmatically to implement a Pong paddle, to draw a rectangle with core graphics. So I have my H file, and thankfully there's really nothing interesting there to worry about. But if I go into my M file, notice that this is how I can fairly simply draw on an iOS device. So much like in Photoshop, the world of iOS is modeled in terms of rectangles, pixels and x-axes and y-axes. And it turns out that inside of a UI view, if you're not using a nib, a drawRect method will get called automatically when that view is created. So in other words, when I instantiate a paddle view, this method drawRect will get executed. And its purpose in life is supposed to draw something on the screen. So how does this work? Well, CGRect is another struct. I can hover over this thing with Option, and you'll see that it has an origin inside of it and a size. So that's what defines a rectangle here. And there's this little helper function that allows me to make a rectangle. Specifically, it's going to make it at location 0, 0, so in the very top left-hand corner. And it's going to make it 10 floating point 10 points wide, and it's going to make 60 points tall. So roughly 10 pixels by 60 pixels, though it does depend on the resolution of the screen. So in this case, I now have a rectangle. I want to make this thing white. Well, it turns out there's a UI color class, and I can very easily set things to white for this rectangle just by saying give me the white color and set it. And now notice I'm calling UI rect fill. I want to fill the square that I've just constructed with whatever color I've decided on. So in other words, line 1 creates the rectangle. Line 2 picks a paintbrush out of the available paintbrush colors. And line 3 actually paints that rectangle on the screen for you. So what's interesting here? We're really actually mixing two different languages, right? Line 1 is what language? C. Line 2 is Objective-C. Line 3 is C. All right, so again, Objective-C is layered on top of C, and indeed, a lot of the underlying core graphics routines, a lot of the low-level mechanisms in iOS are still written in C, partly for performance again, partly for other reasons. So understanding the syntax, which is essentially the same, except you don't have object-oriented features in the older style C code. All right, so that gives us our paddle. What actually gives us the dynamism? Well, we can do this. So notice that I've done this here. Let me wave my hands at this a little bit, just so we don't get too distracted. Here's my init method for the actual game. This is the view controller. Notice at the very top line, I'm allocating a paddle view, and I'm giving it an init with frame message that's saying 10 by 10 by 10 by 60, which is just giving it a region of the screen to operate within. And then I'm effectively having it draw itself within that region, a sliver of the screen on the left-hand side. And then what is the second and final line there doing? Self.view, add subview. Well, GUI programming, at least in iOS, is entirely about hierarchy and layering one thing on top of another. So you recall in Interface Builder, when we've been dragging and dropping things, recall that they start creating a hierarchy of things on the left-hand side, where you can see that the table view has this button, or rather this UI view has a button inside of it. There's a text view inside of it. So in other words, you're layering widgets and widgets on top of one another, on top of some kind of canvas. And this second line of code there is essentially saying add this rectangle to the existing canvas. And that canvas, by default, is known as self.view. So that's the default rectangle that initially is white. When we do nothing in our application, the add subview is layering something on top of that. Or in this case, I made it black by tweaking the nib. So how do I now respond to the user's finger? Well, it's actually relatively straightforward. I have to implement this special method called touchesMoved with event. And now I simply have to get some details from that object and then move the paddle's location in lockstep along the y-axis. So on the left-hand side here, I have a UI touch pointer, and I am saying give me all the touches that just happened on any object. This is actually a simple application. I don't have to worry about multi-touch. So wherever the user touched, that's the one I care about. So that first line gives me the touch that just happened on the screen. In the second line here, I need to know where did the user touch on the screen. So if I ask the touch object, what is your location in the view, this is going to give me an XY coordinate of wherever the human's finger just went down. The only field I care about there is one of the axes of that finger press. And so over here, notice that I am, again, grabbing the finger's location. Then I'm updating the center of the paddle to be at a new point on the screen. I'm leaving its x-axis unchanged. And by unchanged, I mean just ask the paddle view where its current center is and get x and set it back equal to that value. But location is that of the finger. So I'm saying make your y coordinate match the y-axis of wherever the finger was on the screen. And because these events are being fired continuously, again and again and again, every few milliseconds, you have the visual effect of the paddle actually tracking the finger up and down. So how do we actually now make a game out of this? Well, we have the beginnings of the user playing. Now all we need is the ability to play against a computer. So let me go ahead here and open up Pong. And in Pong, just to spoil the effect, actually, let's not spoil the effect. It'll be a better cliffhanger if you see the end result first. So this time, just to spice things up a bit, I decided I don't want to draw the paddle by default by hand. I don't want to draw the ball by hand. I have Photoshop. I'm going to make these things myself. So I made here the paddle, which looks like, you can barely see it. Can you see it on the projector? No, but it's over there. It's white. It looks really good, though, on this screen. And now you're really not going to see the ball. I'll put the arrow at the ball. It's like a 4-pixel ball right there. OK, so that saved me a lot of programming effort. And frankly, it did. It's a lot easier to make a few pixels in a graphical editor and save them as a PNG or a JPEG. So that's what I did, though it's not strictly necessary. So how does this program get kickstarted? Well, here's my app delegate. It is calling, as usual, it seems, init with nib name. So let's go down now to my nib. And the nib, OK, so I have some stuff going on here. So this thing, and this thing are actually UI image views. So they're the same things as I used for Tommy before, but I scaled them down so that they don't fill the whole screen. So that's just where I put them by default. But we'll be able to move those image views because they're actually wrapped, again, in an object. Score left, score right, these are actually just UI labels. And I just aligned it in such a way that those words will disappear. They'll be replaced with actual numbers as score is actually kept track of here. So now if I look over in my view controller, let's see, actually, in my view controller, I have a kickoff method, which is interesting. That'll kick off the game, apparently. And now here I have a whole bunch of stuff inside. So quick tour. I have a constant declared up here. You might recall from C that you can use sharp define to declare constants. You still can in Objective-C, but what's better about this declaration of a constant versus the sharp define? Yeah, so this actually has a type associated with it. Sharp define simply does a find and replace throughout your code, which means there's no notion of type checking there. By declaring it as an actual const, it means I get all of the privileges afforded to a float in this case, so I can't misuse this or use it in the wrong location if something expects that particular type. Here I have an ivar that's of type CG_point to keep track of velocity, and velocity here will ultimately be initialized to this and on an x-axis and a y-axis. So a vector is velocity. I have a whole bunch of private properties, and most of these you can infer what they are. A pointer to the left paddle, the right paddle, the left label, the right label, the ball, score left, score right. And then also I implemented a pause feature so that if you background this application, it will actually pause the game and then reload it wherever it left off. Now I'm doing some boring synthesizing of all of these properties down here. So let's actually see what happens when I initialize this application for the first time. So 1, I'm initializing the scores to be 0. That's reasonable to do once and only once. 2, I'm initializing the ball's velocity to be a CG_point make. So velocity comma velocity, you can represent a vector with effectively a point. You just need an x component and a y component to represent that vector. So I'm just doing that to say we're going to go the same speed along the x-axis as you are on the y-axis. So that even as I change the ball's orientation, it's going to always go in the same speed. And now we need this timer. So just like in JavaScript, if you want to do something cyclically, listening for events, this thing's going to listen every 0.05 seconds for some kind of interaction on the screen. I need to essentially constantly check, is the ball touching the paddle? Is the ball touching the paddle? Is the ball touching the paddle? Or did it go off to one of the sides? I need to keep checking that, just like in Scratch, if you use that language a year or more back. So let's fast forward down to any view. And this is all I have for view. In this game, because I've constructed a lot of it in the nib, I don't need to do as much in view did load. But I do need to start the game when the view comes into display. So after view did load, you automatically call it as a method called view did appear. So just because it's been allocated doesn't mean the user can see it. When the user can actually see the state of the world, this method's invoked. So I'm going to pass the kickoff message to myself. So let's follow this these breadcrumbs to kickoff. Scroll up, scroll up, scroll up. All right, so kickoff. So by default, the game is going to be paused. The ball is going to be positioned in the middle of the board, and the gameplay will be paused. I'm going to update the scores to be equal to, and here's where we just have to do a bit of NSString math. I have a score left property, which is a number, an integer, and a score right. So I just need to convert those to strings so that I can display them on the screen. Here's how I'm going to center the ball. I'm going to locate it at 240, 160 pixels or points on the screen. And then I'm going to line the paddles. And this was a bit of trial and error, but I decided that this is where I want the two paddles to start, on the left side of the screen and the right side of the screen. Now, when the user actually starts moving, gameplay is going to be invoked. So the play method, the play method is going to be invoked every 0.05 seconds. So long as the game isn't paused, and the game will automatically be unpaused once the user starts interacting with the screen, thanks to some code, play is going to get invoked constantly, again and again and again. Think of that event loop that we talked about at the start of today. If the game is paused, don't do anything. Just return, and we'll ask the question again in a few milliseconds. Otherwise, go ahead and move the ball. And this is very similar in spirit to what we did with the paddle. But in this case, I want the ball to be self-propelled. So I'm going to move the ball from its current x coordinate plus the x velocity, comma, the current y component